Hi, this tutorial is going to be on the intrinsic conduction system of the heart and how that then relates to the events that you see in an electrocardiogram or ECG. The intrinsic conduction system is a network of autorhythmic and conductive cells that distribute the depolarization to the proper parts of the heart so that the contractions that follow are then coordinated and timed properly. The parts of the intrinsic conduction system can be seen here, 1 through 5, and we're just going to run through them real quick and trace the flow of depolarization through these conductive fibers. It is going to start at the sinoatrial node, which is the pacemaker of the heart. These are the autorhythmic fibers that spontaneously depolarize to set the heart rhythm. So that depolarizes first. This depolarization is going to spread, as the arrows indicate, across the atria through gap junctions from cell to cell. They will next hit the atrioventricular node, located in between the atria and the ventricles. It is here that the depolarization will pause for approximately 1/10 of a second before it goes on to enter the atrioventricular bundle, AV bundle, or bundle of His. So that is this part right here, which electrically couples the atria to the ventricles. You should remember that here and here on the outside surfaces of the heart where the atria meet up with the ventricles, there's some connective tissue that prevents depolarization from spreading down the ventricle walls from the atria. So you have the bundle of His is going to split into these two bundle branches. If I skip that slide right there. So now we're in the two bundle branches, which just carry the depolarization down to the apex of the heart, and then the Purkinje fibers run up the ventricle walls so that the ventricles start their depolarization at the apex, and then the wave of depolarization spreads up the sides of the ventricles so that the contraction will then start at the bottom of the heart, run up the side of the ventricles, and then blood will be squeezed up from the ventricles into either, here would be the aorta, or the pulmonary semilunar valve on the other side of the heart. So that is your intrinsic conduction system. I'm just going to skip through a couple slides here and move on to how these electrical events are displayed graphically when you hook up electrodes to somebody's body and perform an electrocardiogram or an ECG. You should remember that the ECG reflects changes in the electrical field of the body as measured by electrodes and not necessarily membrane potential. They look very similar because they're a graph with lines going up and down, but they are different things. So for the ECG, first you just want to get down what the three different waves represent and where on the ECG you get depolarization and repolarization of your atria and your ventricles, and then we'll overlay the events of the intrinsic conduction system on top of what we already know about the ECG. So just looking at the ECG, the first deflection wave that you see is the P wave. This is caused by atrial depolarization. When the ventricles depolarize, you get the QRS complex. At the same time as the QRS complex, you will get repolarization of the atria. However, that is not represented by the QRS complex. Then you get this brief flat line here, followed by the T wave, which is ventricular repolarization. So you have atrial depolarization at the P wave, ventricular depolarization in the QRS complex, atrial repolarization at the same time, but not represented, followed by the T wave, which is ventricular repolarization. So now we can put together the spread of depolarization through the intrinsic conduction system with the ECG and get what is essentially one of your big essay questions. It is going to start at the SA node, which is the pacemaker of the heart. This spontaneously depolarizes. That depolarization is going to spread from cell to cell across the atria. This causes the P wave. The depolarization will then be briefly delayed here at the AV node. That is represented by this little flat line here. After the pause at the AV node, the depolarization will spread into the bundle and then bundle branches and Purkinje fibers. So you get the QRS complex, which is the depolarization of all the parts of the ventricles. You will note at the same time you've got repolarization of the atria. Red here means repolarization. So atrial repolarization takes place at the same time as the QRS complex, but is not represented by the QRS complex. So next you get this little flat line on the ECG, which is the pause before the ventricles start to repolarize, and then the repolarization of the ventricles is represented by the T wave, and once the ventricles have fully repolarized, you're here at the isoelectric or flat line there. And that sums up everything. We can run through it one more time just for a little bit more practice. So we're going to start at the SA node, which spontaneously depolarizes. This depolarization spreads across the atria, causing the P wave. That depolarization pauses briefly at the AV node, causing this little flat line, and then the depolarization is going to spread through the bundle branches, and Purkinje fibers. This is going to cause our QRS complex. At the same time as the QRS complex, you get repolarization of the atria. Once the depolarization has spread throughout the ventricles, you get repolarization of the ventricles represented by the T wave, and then once the ventricles are fully repolarized, you have a return to the isoelectric line. And that ties together the flow of depolarization through the parts of the intrinsic conduction system and how that flow is related to the events that you see on an electrocardiogram, all done under 10 minutes.